Already we have started characteristics of MOSFET, under which we have studied finite output resistance, then we have studied input impedance, sub-threshold conduction, avalanche breakdown. All these parameters we have studied in the previous lectures, right? Input impedance of MOSFET is ideally infinity and output impedance of MOSFET is ideally zero, but there remains some dynamic impedance of output, and which is given in the graph. You will see this graph. This particular graph is related to output resistance, and from this graph itself we can find out output impedance. The slope is given by 1 upon Rho, and which is constant. Normally the rate of change of ds upon id, delta vds upon delta id, is called output resistance of the MOSFET. Input impedance is also infinity. This output impedance is normally very low in the MOSFET. Input impedance, second thing is input impedance of MOSFET, which is very high, which is given by ZGS, gate to source impedance is normally called a input impedance of the MOSFET. Then we have studied sub-threshold conduction. Sub-threshold conduction means when transistor is connected or it is not in a working state, or in other way we can say that when VGS, gate to source voltage, as per this figure, is 0 or less than threshold voltage. Less than threshold voltage is, means which voltage? It is a cutoff voltage at which in a diode characteristics you will find a knee voltage or cutoff voltage. That point of voltage is called a threshold voltage, and if gate voltage is connected to 0 or less than that threshold voltage, then gate to source or gate to drain transistor, gate to drain is in the reverse bias. Gate to drain is just like a reverse bias, and there will not be any current flow through the MOSFET. MOSFEट मधून कुठलाही गेट व्होल्टेज जर तुमचा 0 असेल तर MOSFET मध्ये आयडियली 0 करंट फ्लो व्हायला पाहिजे. मीन्स गेट मधून 0 करंट फ्लो व्हायला पाहिजे, पण ते तसं होत नाही. ड्यू टू सम लिकेज इन दी n type of material or conductors, due to that leakage a current flows through this gate and it will not be 0. That is called sub-threshold conduction current. Sub-threshold conduction current, it is also called IST. It is also called I sub or I sub current. Means when gate voltage is 0, there should be ideally 0 current through gate and through source and drain, and due to leakage in the materials, this I sub will not be 0 if gate voltage is 0, and I sub is some leakage current which is called sub-threshold conduction. That we have studied in the last lecture. Then we have studied a avalanche breakdown. Avalanche breakdown means it is a reverse bias breakdown, just like a avalanche diode breakdown is there. When diode is connected in the reverse bias, as an example, if when diode is connected in the reverse bias, then there will be 0 leakage current initially, and when that current increases, then diode when voltage across diode increases, reverse bias voltage across diode increases, then drastically that voltage breaks the reverse bias condition of the diode, and there will be a drastic flood of current through the diode, which is called avalanche breakdown current. Same way in the MOSFET drain, if drain is connected to certain VDS, drain to source voltage is connected, say 5 volt is connected across drain to source, which is very high, normally it is very high, which is also called VDD or which is also called VCC. If this is the case, then, and substrate, already we have a P type of substrate and N type of drain is there, N plus concentration of drain is there, and substrate is P. There remains reverse bias junction across P substrate and N type of drain. So this reverse bias condition causes a reverse bias junction across N type of material and P type of substrate, as given in a figure. You will find here this is a wide depletion region. Why there is a wide depletion region? Because this is connected to VDS, which is equal to high voltage, and due to this VDS, which is very high, normally it is 5 volt in a transistor, there remains a wide depletion region, and this, due to this depletion region, there exists reverse bias junction across substrate and drain. This is a reverse bias junction, okay, as given in the figure. And when this voltage VDS increases slowly, when we increase this VDS slowly, this reverse bias junctions breaks. This reverse bias junction breaks and current drastically flows through the drain to source, which is called avalanche breakdown. The same situation occurs in diode as a reverse bias, and same situations occurs in MOSFET also. This is called a avalanche breakdown. This is called a avalanche breakdown. Then we'll switch to next point, that is punch through breakdown. In an avalanche breakdown, we are connecting gate voltage at certain voltage level while VDS is maximum, and in a punch through breakdown you will find that, as shown in a figure, you will find that gate voltage is shorted, that means it is connected to 0 volt, and we are connecting VDS at certain voltage level. That means VDS is VDD first initially, and gate voltage is connected to 0. This is the situation. While in previous case, in an avalanche breakdown, it was gate voltage also connect, certain value was there, and VDS was also there. Here gate voltage is only shorted, and due to this short circuit or 0 voltage gate voltage, there exists a depletion region across whole drain to source channel. This complete is a channel. I am just showing you a channel. This complete is a channel. This is a channel, and in this channel, due to gate voltage 0 and VDS is connected, there exists a depletion region across whole channel. To break this channel, I have to increase this VDS again and again. When I increase this VDS, still further I am increasing this VDS, then drastically current flows through this. So this breakdown is called punch through breakdown. This breakdown of depletion region is called punch through breakdown, and due to which there is a drastic change in current and current rapidly increases through the channel. This condition is called punch through breakdown. Let us switch to next point, which is body effect. Body effect is the difference in potential between body and the source terminal. Body effect means body is substrate and source terminal is source material. So the difference in potential between body and the source terminal causes a change in the threshold voltage of the MOSFET. This effect of change in threshold voltage is called the body effect or the backgate effect. Now I will explain you how this body effect occurs. This is a N channel source. This is N material of the MOSFET and P type of substrate is there. Between these two substrates there occurs a diode. In between these two, as it is a N type of material and substrate is P material, there occurs a diode. When gate is connected to 0 volt and this substrate is connected to 0 volt and source is also connected to 0 volt. So S V as given in figure, then there exists a reverse bias diode between source and P type substrate is a body and N plus is a source. Then there exists a diode material between these two. Now due to this potential difference between source and substrate change in threshold voltage. Each body which is connected to ground, there exists diode is called body effect. So threshold voltage of the MOSFET. If temperature changes, then there exists a temperature diode exists between material, and when it is connected to okay, let me to draw it properly. So there is a difference between this potential difference H voltage to change per degree threshold voltage change is called body effect. If 1 degree then there will be a potential difference between this source and substrate. This potential difference will change if there is 1 degree change in temperature. Suppose there will be change of 0.2 volt temperature change per 1 degree centigrade. So degree centigrade, 0.2 volt change per degree centigrade will occur, and this change will change our VT, threshold voltage will change, because threshold voltage means knee voltage or voltage at which current will drastically change, or MOSFET will enter from cutoff region to active region. This voltage is called threshold voltage, that will change due to this body effect. Next part we will learn is temperature effect. Temperature effect. The next definition is effect of temperature. If there is change in temperature, then there remains change in the conduction. Suppose temperature of any silicon or germanium material changes, then what is impact on the conductivity of the material? The conductivity will also change. For conducting material, if temperature increases, then conductivity decreases, and in the non-conductive material, if temperature increases, conductivity increases. That is, positive change in conduction in non-conducting material occurs. For the semiconductor, the same effect occurs. For the semiconductor, if temperature increases, it is negative temperature coefficient of material. If temperature increases, there will be less conductance, or resistance will increase. Conductance will decrease in the semiconductor material. Conductance will decrease and resistance will increase. That is, negative temperature coefficient of conductance is there if we consider a semiconductor material. Same thing occurs when there will be change in temperature, then drain to drain supply, this is source, it will also change. Substrate type of material will also change, and conductivity of these materials will change. Drain conductivity will change, and substrate conductivity will also change. I am explaining you a temperature effect. So what changes will occur? For the temperature effect, there will be a change in threshold voltage or conduction in the drain. So there will be 0.2 volt change per degree centigrade due to temperature. That means resistance will also change. So this resistance, what is impact on resistance of this drain, and substrate resistance will be there. What is impact on resistance? Resistance impact will be, for an example, if temperature is 75 degrees and this drain to substrate material having 50 ohm resistance in between these two, at 75 degrees centigrade, if it is sorry, I'm again changing it. As temperature changes, drain and substrate resistance R between these two will also change. So R, what changes occur? R at 75 degree is, say 75 degree, it is around 50 ohm. 50 ohm. If temperature is increased to 125 degrees, then resistance R changes, R becomes 100, around 100, because as temperature increases, conductivity decreases but resistance increases. And so if R is equal to 75 degree, 50 ohm resistance is there between drain and substrate, that increases to 125 degree, around 100 ohm. All of you got it? If temperature of MOSFET increases, then resistance also increases. As resistance increases, for an example, I have given you example. If temperature is 75 degree, R is equal to 50 ohm. This is T and this is R. Where is R? R is resistance between drain and substrate. If temperature is 125 degree, then resistance will become 100 ohm. So this is change in the MOSFET characteristics or resistance due to change in temperature. Now we will learn last part from these characteristics, that is W by L effect, body width to length effect of the transistor. I will draw it at the last. Width W by L effect. W by L effect means what? See, W by, for this, here I will explain. Here I will explain W by L effect. Yes. Screen is not visible. Okay. I will show you again. Okay. Actually, what happened? 40 minutes are over. That's why screen became invisible. Now, is it visible? Just check. Is it visible now? Is it visible? Okay. I'll finish it immediately. Last point I am going to learn, that is W by L effect. W by L means width. See, this is width of the channel, and this is total length of the channel. This is length and this is width. This is width of the channel and this is length of the channel between drain and source. I'll go up to show you. Here it will be clearly visible. This is width of the channel. This is W, and this is length of the channel. Okay. If W by L ratio will change, means L length is fixed. Suppose drain and source should not be at higher distances. This is the case. This is the requirement. So irrespective of L, W by L ratio, if length is fixed, say 2 centimeter, which is fixed, and W is also less, this if ratio is less ratio or this decreasing, amplification factor will be less, current amplification factor will be less, because width is less, current, it will not fetch more current through the channel. If increased W by L ratio, more, say more ratio, ID will increase. Okay, ID will increase. If ratio W by L increases, means length is less and width is more, then current flowing through drain and source will increase. So this is W by L. There will be a question on definitions of body effect, temperature effect, sub-threshold effect, sub-threshold conduction, then input impedance, output impedance, transconductance, W by L effect. These are the few characteristics of MOSFETs, and there will be a question of 8 marks on these characteristics. Now last characteristics was W by L, where if current is less, W by L ratio is less, current ID will flow less through the channel. If W by L is high, then current will become higher, or there will be a current, more amplification of current. So in a MOSFET there should be more W by L ratio. Okay, got it? So all these characteristics or on these parameters, there will be a question in the question paper like draw and explain this and this. If it will be a 8 marks question, it will fetch 2 marks each. Okay, we will stop here today. Tomorrow we will see next part. Tomorrow we will finish this unit. That is last point we will see tomorrow. That is common source. Okay, you can leave now. Finished, all of you?